So now we move to spherical coordinate system, where we have a rho, a theta, and a phi. So those are our coordinates. Let's take a look at the picture here. Rho will be the radial distance out from the origin to the point out in space. Different from R. Remember, R is the radial distance in the xy plane out to a point that's in the xy plane. The theta is the same theta as it was for polar and cylindrical. It is the positive angle swung from the x-axis. And now we have a new angle called phi, which is the positive angle swung down from the positive z-axis. And so rho, theta, and phi are our coordinates in that order. The second one's going to be theta, third one's going to be phi. Alright, to help us figure this out, what we're going to do is take a look at this. This is really just one triangle. One leg is R, the other leg is Z. So we have one leg Z, the other leg R, and we have the theta phi. Or the angle is phi. And so we're looking at basically this version of the triangle here. And using trig, we can get the equations that we need. Figure out how things are related. Pythagorean Theorem will tell us first that z squared plus r squared is rho squared. But we know what r squared is. R squared is x squared plus y squared. So rho squared would be then just x squared plus y squared plus z squared. That's what you would think. This distance at the point is from the origin. Rho is that. So rho squared is the square root of that. Alright, great. Rho squared is, rho is that, the square root of that, and rho squared is the x squared plus y squared plus z squared. Great. Now we go to trig, and we look at phi, and use sine. The sine of phi is the opposite, r, or the hypotenuse, rho. So r is rho sine phi. Well, that's going to be our connector. We know that in polar, the theta and the r give you the x. Right? X is equal to r cosine theta. Well, the r will get replaced now by rho sine phi. So x is rho sine phi, now cosine theta. Remember y? It's r sine theta. Well, now it's going to be rho sine phi sine theta, because that's what r is. What about z? We'll go back to the triangle, and instead of using sine, we'll use cosine. And we get that cosine of phi is z over rho. So solving for z, we get that z is rho cosine phi. And these will be our connecting equations that will help us figure out how to go from coordinate system to coordinate system. Theta is the same theta as it was back in polar. That's the tangent of theta, tangent of theta is y over x. So we take the arctan to get the theta, the arctan of y over x. And now we have this phi, and it's going to be arc cosine of z over rho is one way to look at it. All right, great. Now let's talk about phi. Phi is 0 when you're at the positive z-axis. And then phi is this angle that you swing down from the positive z-axis. So by the time phi is at pi over 2, then you're at the xy plane. 90 degrees down from the z-axis is the xy plane. And then we're going to go and continue phi past pi over 2. And when phi is pi, 180 degrees, you're at the negative z-axis. And so we're not going to let phi go anything past that. So from 0 to pi will be the range on phi. And theta is the same from 0 to 2 pi as it was. And this creates spheres, spherical coordinates. So now the question is, well, what happens to dv? Like in polar, dA became r dr d theta. And the way we worked that out is we looked at the Jacobian of the transformation. So now let's do that again. We have that it turns out that dv is rho squared sine phi times d rho d theta d phi. Here's the sort of geometric way to see it. Infinitesimally, this will look like a cube, and there'll be 3 dimensions: the length, the width, and the height. And it turns out that the height will be considered as d rho, the change in radius. The thickness here is this distance here, and that's a piece of arc length. And then we have the other distance is the distance here. And it turns out that what we have is rho squared sine phi, d rho d phi d theta. To understand it better, let's just go with the Jacobian. Remember how we do the Jacobian? We have to take the equations x, y, and z and use them to find the Jacobian by taking partial derivatives. Partial with respect to x, partial derivative of x with respect to rho, partial derivative of y with respect to rho. I'm sorry, let's keep it at x. Partial derivative of x with respect to theta, and partial derivative of x with respect to phi. So we drop the rho to get this rho derivative. We drop the sine of phi becomes theta. The cosine of theta has negative sine of theta as its derivative, so we get that. Sine of phi has cosine phi as its derivative, so we get that. Then for y, we drop that and we get sine phi cosine, sine phi sine theta. For theta, on the y derivative, we get cosine theta sine phi, with the rho still there. And for phi, we get cosine phi sine theta. For z, we take the rho derivative, we get cosine phi. There's no theta in z equation, so 0 for that derivative. And then we get negative rho sine phi for the phi derivative. We throw these into a matrix and we find the determinant of that matrix, each guy being a rho. And we get a lot of cancellation. It works out nice. It looks pretty bad, but it actually works out nice. What we can do is take advantage of the power of determinants, and we can expand about any row or column, and we take advantage of the 0 and expand about the third row. And so we have cosine phi, and then we use this subdeterminant here, which is negative rho squared sine squared on theta sine phi cosine theta. And then we have minus rho squared cosine phi sine phi, and then cosine squared on theta. Okay. Now, we have 0 times the middle subdeterminant, and then we have minus rho sine phi times this subdeterminant, which is rho sine squared phi cosine squared theta plus rho sine squared phi sine squared theta. So there's a lot going on here, but I think actually it's best if we rearrange these two terms. But anyway, we actually get a lot of cancel. We factor out what they have in common, and we get a lot of cancellation. In this bracket here, these guys share a sine of phi and a rho squared, and the cosine of phi. So when we take that out, along with the negative, we end up with cosine squared plus sine squared. Like basically they share all of this in common, cosine squared and then plus the sine squared. So that's just a 1. We had the cosine phi already out. We took out a rho squared, we took out a negative, and we took out a sine of phi along with the cosine of phi to make it cosine squared here. And it's convenient, we're left with a 1 there. On this guy, what do they have in common here? They have a rho and a sine squared on phi. Take that out, you already have a rho and a sine on phi. So we have a minus rho cubed, minus rho squared, sine cubed on phi, and conveniently left with cosine squared plus sine squared again. So that's 1. Now you have these two guys, where you could factor out what they have in common, which is a minus rho squared sine phi. and you'll conveniently be left with cosine squared phi on sine squared phi added together. So we end up with a 1 there. So the Jacobian is a negative rho squared sine phi, but remember, you're supposed to take the absolute value of the Jacobian. We end up with rho squared sine phi. So that is the extra element of area that needs to be put into the dV formula. You can't just change dx dy dz into d rho d theta d phi. We have to add on this rho squared sine of phi. And so rho squared sine of phi, then d rho d theta d phi. Okay, we proved it with the Jacobian here. Here's a visual. If you want to work that out, you can. You can see how the different dimensions end up being these values here. And then we have the product of these three values here, here, and here. Length, width, and height. Here's height, here's length, and here's the thickness of it. And the product of these will be rho squared sine phi, d rho d theta d phi. But anyway, we have it. We have the Jacobian, and now we're ready to use it to be able to integrate in spherical.